Good afternoon. This presentation will provide you with a brief summary of some recently completed work that was done here at the USGS, as well as with our partner agencies listed at the bottom of the slide. It was a cooperative effort among these many agencies, and we refer to this project as Water for the Seasons. The main USGS contribution to this effort was led by Wes Kitliston, and because he's moved on, I'll be presenting on Wes's behalf today. As you can see from the title of the talk, I'm going to be focused on the potential impacts of warming within the upper Carson River watershed, so from the headwaters to the outlet of Carson Valley. And here's a map of that general area that I'm talking about. The region that is outlined in purple is where I will be focused on for this talk. Roughly 40% of the water that enters Carson Valley leaves as ET from irrigated crops, and that comes from a report published in 2006. Historically, snowpack has served as the main source of water for the upper watershed, and there is no feasible locations for additional surface water storage in the upper watershed. There is, in the past, the work that was done to investigate the feasibility of Watashimu Reservoir, but of course that was never realized. There is a complex irrigation system that relies heavily on return flows and itself providing recharge to the groundwater system that then may flow back to the river and sustain the river as groundwater discharge. Water use along the Carson River may have far-reaching impacts, and that is because of the administrative and physical link between the Truckee and Carson River systems that we refer to as Truckee Canal. So to the extent that flows at Fort Churchill are impacted, that could impact the Truckee River system via the Truckee Canal, as more or less water may be brought across the Basin Divide. So future concerns facing Carson Valley and indeed the entire Carson River watershed, as things warm up, that reservoir, that snowpack in the upper reaches of the watershed may in fact dwindle. And that could be because precipitation falling in the form of rain rather than as snow, or just that snowpack being closer to the point of melting and therefore generating stream flow much earlier in the year than what the system is historically used to operate the system. To facilitate this study, we've applied two models. In fact, these two models have been tightly integrated, as I'll describe in a moment. The first model applied is GSFLOW. GSFLOW handles all of the physical hydrology in the simulated watershed. For example, it is going to simulate rainfall runoff processes, build up a snowpack, maintain an energy balance for melting the snowpack, and so on. GSFLOW will also generate streamflow hydrographs corresponding to these processes. Equipped with the simulated runoff, we can then distribute that supply among the various water demands spread throughout Carson Valley. Of course, the predominant water use in Carson Valley is agriculture, but other demands like municipal and industrial use can be supplied as well. The second code that is being used to help us with this study is MODSIM. MODSIM is a river operations model and is different from GSFLOW in that it is designed to figure out how to allocate a limited water supply among a competing set of demands that are spatially spread out and have varying levels of priority. In other words, when the river cannot supply all of the competing demands and goes into regulation, MODSIM will first curtail the more junior water rights in favor of supplying the more senior water rights first. And as supply continues to diminish, the next most junior water rights will be curtailed, and so on. Whereas MODSIM was specifically designed to address the supply and demand problem, GSFLOW has no notion of relative water priorities, and in fact on its own cannot make decisions about how to divert water. It must be informed on how to divert water by MODSIM. And that, in a nutshell, is the beauty of the integrated code that has been developed and applied for this study. The link node network at the bottom of the slide depicts MODSIM's view of the world. That is, individual water rights can be assigned relative priorities, And as water makes its way through the network, MODSIM will turn on or off diversions to these priorities depending on the available supply. One last note about the integrated code. Because GSFLOW and MODSIM have been tightly integrated, the locations and magnitude of the groundwater return processes affecting future water deliveries and are themselves rooted in the past or in the history of previous water deliveries, this is far more accurately represented than if we only applied MODSIM to our problem. In short, by integrating and then applying these two codes, we end up with a simulation that is greater than the sum of its parts, in my humble opinion. And so with our integrated hydrologic river operations model in hand, we are going to go ahead and apply this to Carson Valley. If I may first call your attention to the figure on the right, this is a depiction of the MODSIM GSFLOW code. On the top is the link node network of MODSIM, and that is going to switch on or off diversions depending on who's in priority and how much water is in the river. And it can also account for things like reservoir storage accounts, which we don't have in Carson Valley. And then below that is our distributed parameter physically based hydrologic model, in our case GSFLOW. And so that particular model is going to account for crop use, crop water use, things like ET. It's also going to account for pumping and the effect that those pumps have on groundwater surface water interaction. And so by accounting for all of these influences on flow in the river, the MODSIM network will respond by shutting down or turning on diversions as it needs to in order to satisfy as many water rights as it can. So we can take that code and apply it to Carson Valley there on the left. And just to provide a brief description of how the model is set up for Carson Valley, you can see the different land parcels that are highlighted by different colors based on when the water rights were allocated. So the warmer colors are more junior to the green or greener colors. And here is what the MODSIM network that was developed for Carson Valley looks like on the right. And so there are approximately 546 individual water rights represented within our MODSIM network. So why is that important? Well, as flows increase or decrease in the river based either on snowmelt from the upper watershed or from pumping within the valley itself, MODSIM is going to respond to those effects by turning on or off diversions to these individual water rights based on their priority. Before we can apply the integrated hydrologic river operations model to any scenario that we may be interested in investigating further, we first need to calibrate it. Model calibration is undertaken to ensure that what the model is simulating matches with reality. So we may, for example, manipulate the hydraulic conductivity field of the aquifer or the storage of the aquifer in such a way to ensure that the simulated groundwater heads match observed groundwater heads, or that the simulated stream flow matches the observed historical stream flow. We can do this for any number of observations that we may have. Something that we have classified as innovative would be using the estimates of actual crop water use that Justin Huntington provided us with and ensure that the model is roughly producing or simulating those same crop water use volumes. And in fact, we did that to help improve our calibration. Satisfied that our model is calibrated, we can then use it to investigate the impacts of various scenarios. And in fact, for this study, we ran 5 scenarios. The first scenario warmed up the GSFLOW model by 1 degree Celsius, and the 5th most extreme scenario warmed up GSFLOW by 5 degrees Celsius. In all 5 scenarios, we held precipitation constant while altering the temperature. So the result of this is going to be what was snowfall in the baseline simulation may convert to rainfall depending on how much warm-up it takes to do that. And so the various scenarios will get at that for us. The net result is, of course, that the stream flow exiting the mountain block and entering Carson Valley is going to have a much earlier timing. And the next slide gets into that. Justification for our warm-up scenarios comes from the fact that roughly 30 individual global circulation models are predicting warmer temperatures for this region. And you can see those predicted temperatures in the plot in the upper left. There's quite a bit of variability among those different model runs or among those different GCM realizations. However, they are all agreeing that warm-up is expected. And so as things warm up, we're going to get earlier and earlier runoff from the mountain block. And this is depicted in the lower left plot. So, for example, our baseline simulation might predict a hydrograph something like that, which is shown by the darker blue line. And that vertical red line is the center of mass, or the date of center of mass. So roughly half the annual flow is going to be on either side of that vertical red line. And as things warm up and as flow comes out of the mountain block sooner, that hydrograph is going to shift with the left to the left, and with it, that date of center of mass of runoff. We took the GSFLOW model developed for the upper catchment and looked at quarter-degree Celsius warm-ups, and those are shown on the x-axis in the figure on the right. Because there's 35 years of simulation, we can then plot for each quarter-degree warm-up a histogram of when the center of mass of runoff occurs and take the average of those, and that's what you're seeing with that more bold black line. So with no warm-up, or the histogram all the way to the left, the center of mass was roughly at the end of May, beginning of June. And then as we warm things up all the way to, let's say, 4 degrees Celsius, the center of mass of runoff is now about the time of the spring equinox, so in late March, early April. We can also investigate the impact that warm-up has on mean monthly stream flows. Here we can see that January, February, March, April all have higher mean monthly stream flows in response to warming, whereas stream flow diminishes with warm-up in May, June, July, August, September, and October. This slide is showing the same thing as the previous slide, the difference being that all 5 scenarios have been differenced from the baseline scenario. So here you can just see the relative difference to the baseline. In this slide, as well as the next 3, model results are presented spatially. Here you can see 5 individual panels corresponding to the 5 different warm-up scenarios. This slide is showing decreases in surface water delivery to each of the water-righted parcels expressed as a percentage. As we would expect, the greater the level of warm-up, the greater the shortfall in surface water delivery to the various water rights. In the plus 5 degrees C panel, the black oval is highlighting the model's ability to distribute the available surface water supply while also honoring the relative water right priorities near the confluence of the East Fork and West Fork. For the senior water rights near the confluence of the East and West Forks, the plus 5 degrees C warm-up scenario results are showing a decrease in surface water delivery of over 25% downstream of the confluence of the East and West Forks, about 20 to 30% along the West Fork, but less than 5% along the East Fork. This result is reflective of the relative priority within the different administrative segments of the Carson River being well represented by the model. I'd also like to point out that this represents an important leap forward in our ability to represent irrigated systems like Carson Valley. That is, apart from an integrated hydrologic river operations model like MODSIM GSFLOW, it would be nearly impossible to appropriately route the available surface water supply to the senior water right holders at the end of the East Fork segment. Carson Valley, like most western irrigated systems, is a conjunctive use system. That is, as surface water supplies decrease, irrigators often turn to groundwater to make up the difference. Within the integrated model, supplemental groundwater rights are dynamically kicked on as the surface water supply decreases. To a large extent, supplemental groundwater rights have historically not been exercised to their full permitted levels. Thus, to make up for the surface water delivery shortfalls depicted in the previous slide, the model will pump additional groundwater to offset some of the shortfall. Here we can see that the model responds to additional warm-up with increased pumping. The units in the legend are thousands of cubic meters. And for reference, 6,000 cubic meters of water is roughly equal to 5 acre-feet of water. In the most extreme cases, the simulation extracted an additional 200 to 300,000 cubic meters of additional water over the 35-year simulation period. This averages out to roughly 4,700 acre-feet of additional pumping per year. Another way to express model results is to show the impact of the warm-up scenarios on simulated consumptive use. As I mentioned earlier, the model was calibrated to estimates of actual ET, themselves calculated by the metric model. The estimates of historical ET were furnished by Justin Huntington with DRI and are available from the state engineer's website. Because the baseline simulation was calibrated to historical ET, we have some confidence in the model's ability to predict changes in crop water use under the warm-up scenarios in response to decreases in surface water delivery. Crop water use is often used as a surrogate for crop yield. Thus, decreases in crop water use are indicative of decreases in crop yield and by extension correlate with decreases in the economic output associated with the cropped areas. In the 1 degree C warm-up scenario, we can see a near uniform drop in crop water use owing to decreases in delivery of up to 10%. In the plus 5 degree C warm-up scenario, decreases in crop water use of up to 44% are realized on at least one water-righted parcel. Moreover, the plus 5 degree C warm-up scenario is showing significant and widespread decreases in crop water use along the East Fork. So, what does all this mean? In the preceding slides, we saw that there are decreases in surface water delivery that is in turn going to lead to or contribute to decreases in recharge from surface water irrigation. To compound that, irrigators have supplemental groundwater rights that they can turn to offset those shortages in surface water delivery. So of course this leads to an increase in pumping to meet the crop water demand. So overall, these two things together are going to act to decrease the overall groundwater storage within Carson Valley. And here we can see where those decreases in groundwater storage are occurring. The panel all the way to the left are showing pockets of decreased storage in groundwater to the tune of roughly 40,000 acre-feet. Then we can see those pockets of decreased storage growing as we move right. And in the rightmost panel, the plus 5 degrees C scenario, we can see the most or largest decrease in groundwater storage, roughly 75,000 acre-feet less than in the baseline simulation. And I should mention that all 5 scenarios were differenced with the baseline simulation to arrive at the results we're showing on this slide. The color intensity is showing where the decreases in storage are greatest. The final results slide that I'll be sharing with you is showing the increase in outflow from Carson Valley under the 5 modeled or investigated scenarios. And we can see here that not all the news is bad, depending on where you are in the system. Because we held the amount of precipitation falling in the headwaters the same, but only altered the temperature, what this is telling us is that the runoff generated in the mountains is flowing through Carson Valley prior to the start of the irrigation season, and therefore providing more water to points downstream. And so as we increasingly warm up the upper watershed, we're going to have very little snow pack and certainly very little snowfall in the upper watershed, contributing to mostly runoff that will traverse through Carson Valley prior to the start of the irrigation season. To quickly summarize the results of our model investigation, we found that as we warmed up the GSFLOW simulation, there is more rainfall and less snowpack being simulated by the model. And this in turn led to a series of interrelated effects within the model. The first is that there's earlier and higher river flow from the upper catchments entering Carson Valley. In turn, the simulation also predicted a decrease in Carson River flows between May and October. The reduced river flows will result in decreased surface water deliveries to the water rights distributed throughout Carson Valley. And as a result of that, the model would predict that there's an increased reliance on groundwater to offset the reductions in surface water delivery, contributing to an overall decrease in groundwater stored within Carson Valley. And finally, the earlier and higher flows exiting the upper catchments and traversing through Carson Valley prior to the start of the irrigation season led to an overall increase in flows reaching Lahontan Reservoir between January and March. And that is all I have for my presentation today. Thank you for your time.